So, welcome everyone to the fourth lecture or the fourth talk in our seminar. And today Anna will show us finally Soergel bimodules. So you can start whenever you're ready.
Okay, perfect. So welcome to my seminar talk about the introduction to Soergel bimodules. Soergel bimodules provide an algebraic categorification of the Hecke algebra we have seen last week, and they've become a powerful tool in geometric representation theory. On the one hand, these modules are fairly elementary objects and explicit calculations are possible, but on the other hand, they have a deep connection to Lie theory and geometry, and which is not that easy to understand. And they were first introduced by Wolfgang Soergel, a German mathematician in the early 1990s. I will start by explaining some algebraic notations. After this, I will show you the Chevalier-Shepard-Todd theorem and what we can conclude from it. After this, I will continue with the Desmausur's operator and some of its main properties. Before giving the definition of a Soergel bimodule, the topic of this seminar, I will explain the Bott-Samuelson bimodules, and I will finish up my talk by giving some examples of Soergel bimodules and what we can do with it. So just in the beginning, I want to notice that I have quite a lot of definitions and formulas in my presentation, and this is simply because otherwise it would get a little bit too hard to follow, I guess. So yeah, that's why I did that. Yeah, I will start with some algebraic definitions and notations. A Z-graded vector space is a vector space M equipped with the decomposition into subspaces. M is then defined to be the direct sum over all I and Z of M to the power of I. From now on, I'll mostly say graded instead of Z-graded, since in this topic we usually work over integers and it makes it more easy. The graded pieces of M are the M to the power of I, and we usually arrange the graded pieces of M by height. This means that M to the power of I has height I. If an element M of M is contained in some of the Mi, we call it homogeneous, and the element then has degree I. And we could also apply these definitions over other algebraic objects like rings, modules, algebras, bimodules, and so on. Usually there are some additional conditions to the additions above. Given a graded object M, which can be a vector space, module ring, and so on, and I an integer, we can define a new object M with a shifting by I with the graded pieces M of I to the power of j is defined to be M to the power of I plus j. And I've already said that we can arrange the graded pieces by height. So if we now arrange them vertically, and for example, M within brackets 1 is then obtained by shifting M1, and we say that M is obtained from M in brackets with I is obtained from M via a shift in the grading. So we say M with a shift in grading by 1. And just for conventions, if I talk about a submodule of M, I always mean a graded submodule, meaning a submodule of M which is generated by homogeneous elements. And the next definition I want to mention is that we say that a graded R module is free if it has an R basis that consists of homogeneous elements. When wanting to introduce Soergel bimodules, the algebraic structure we need is a Coxeter system, W and S. And as we have already learned, this is a group W and a finite set S of distinct generators of W. Furthermore, we need its geometric representation, V over R, so the real numbers. This means that V is a real vector space with basis alpha S for S in capital S, which is indexed by simple reflections S. This basis these basis elements alpha s, they're called simple roots. Moreover, V has a dimension of absolute value of S and is equipped with a symmetric bilinear form. This means that all simple roots have the same length. This bilinear form, alpha S alpha t, is defined to be minus cosine of pi divided by mst, where m is a symmetric function m, which sends s times s to the natural numbers including infinity, and satisfies that mss is equal to 1 for all s in S, and for s not equal to t, then mst is equal to mts, hence the matrix that consists of all the mst is symmetric with the entries a natural number greater than 1 or infinity, and we've already seen that in the weeks before. We can then say that the group W consists of the span of all S in capital S, such that St to the power of MST is equal to the identity for any S and T in S. And we have already defined action S of W on V, where the elements are S in capital S, and they are called simple reflections and are of order 2. And this is going to be important. This action is defined to be S of alpha t is equal to alpha t minus 2 times alpha s alpha t, the bilinear form from the before, and times alpha s. Yeah, now let I be a subgroup of S. We can then define the standard parabolic subgroup Wi, which is generated by I, and is a subgroup of W. And this is also a Coxeter group with the representation that St to the power of MST is equal to the identity for any S and T in this I. And if a parabolic subgroup is a finite group, we then say that I is finitary. Let R be the symmetric algebra of V, and this means that R is the symmetric group of V, which is equal to the direct sum over I of all the symmetric groups. Yeah, and knowing that, we can find the ring of Wi invariance of R, which we know by Ri. So yeah, we can write this that Ri is the set of all f and R, such that W times f is equal to f for all the W in Wi, and Rs, which we often also write as Rw, are the invariants under the entire Coxeter group. We write R with a small s instead of R with like the set when we denote that S is a set. Yeah, because S are elements, and that's clear, so it's not necessary to write in brackets. Yeah. So after all these definitions, I will now continue with the Chevalier-Shepard-Todd theorem, which is often also denoted as CST. It states that for I, which is a subgroup of S, and I finitary, then Ri is a polynomial ring. Here, Ri is the polynomial ring over R with the variables Z1, Z2, and so on. These variables commute but don't have any other relations. So the elements of Ri, which are I invariant polynomials, they build a polynomial ring no matter what I is. It only needs to be finitary. Second, R is then a graded free module of finite rank over Ri, and hence Ri is a polynomial ring in finite many variables. To be formulated in different ways, ring of invariants of a finite group acting on a complex vector space is a polynomial ring if and only if the group is generated by pseudo-reflections. But what is a pseudo-reflection? So this is an invertible linear transformation G of V, such that it has finite order and such that its space of fixed points is a subspace of dimension n-1, hence a hyperplane. And here n denotes the dimension of V. We can say that the Chevalier-Chapertard theorem is the algebraic foundation upon which the theory of Soergel bimodules is built, and also kind of a generalization of the theory of symmetric polynomials. Now I'm going to demonstrate the statement of the Chevalier-Chapertard theorem in an example. Let W be the symmetric group S5, which acts on the polynomial ring over R with the variables x1, x2, x3, x4, and x5. Let I be the set of three simple reflections, and then we have that Ri, which is again a polynomial ring and is over the 5 variables you can see here. So x1 plus x2, x1, x2, x3 plus x4 plus x5, x3, x4 plus x3, x5 plus x4, x5, and so on. And those 5 are algebraically independent generators, and they are also in different degrees. Moreover, Ri is, it's then again a polynomial ring where there is no relation between these generators from above. I will now continue with the de Mazur operator. For that, recall that I've already defined that S of alpha t is equal to alpha t minus 2 times alpha s alpha t times alpha s, where the Bilinear form was defined as minus cosine of pi divided by mst. Let WS be an arbitrary Coxeter system. Then for every S in capital S, R S is generated by alpha s squared and the elements alpha t plus cosine pi divided by mst times alpha s. And this is true for all t that are in S, but not small s. Hence, R can be written as the direct sum of Rs and Rs alpha s, and is therefore a splitting of R into S invariants and S anti-invariants. An element is said to be S invariant if S times F is equal to F, and S anti-invariant if S times F is equal to minus F. So the polynomial f in R can uniquely be written in the form f is equal to g plus h times alpha s, where g and h are both in Rs. And with the de Mazur operator that I will give you next, g and h can be found explicitly. So now let S be an element of S. Then the de Mazur operator delta S is a graded map from R to Rs with a shifting grading by -2, which sends F to F minus S of F divided by alpha S. First, we'll check that the S anti-invariants are generated by alpha s, and indeed we have seen this before with the fact that we can write R to be the direct sum of Rs and Rs alpha s. And since this is the case, we can conclude that F minus S of F is divisible by alpha s, hence delta S is well defined. Moreover, we can say that the fraction F minus S of F is S invariant, since both the numerator F minus S of F and the denominator alpha S are S anti-invariant, so the whole fraction is S invariant. We can compute that for any F in R, that delta S of F alpha S is equal to F plus S of F, and this is because after we plug in the definition of the de Mazur operator, that S of f alpha s is equal to minus alpha s of f, when we basically take out the alpha s of the s function. And we then can cancel out the alpha s and we get the result. For alpha s, delta s of f, which is equal to f minus s of f, we get this result by also plugging in a definition and then by simply canceling out alpha s. If we now solve the first equation for s of f, we get, yeah, I've written it down here. And then by inserting this into the second equation, we get that alpha s delta s of f is equal to f minus delta s of f alpha s plus f. And by solving this equation for f, we get that f is equal to delta s of f alpha s divided by 2 plus alpha s divided by 2 of delta s of f. And we can follow from this that f can be written as the sum of its invariant and anti-invariant parts, and this is a very important property. We can express this explicitly by the isomorphism that goes from R to the direct sum of RS, and RS with a shifting grading of -2. And this isomorphism is defined to send f to the pairing delta s f alpha s divided by 2 and delta s of f. And the inverse of this isomorphism is given by that the pairing g and h is sent to g plus h alpha s divided by 2. And this implies that the de Mazur operator can be used to make the RS module, splitting R into the direct sum of RS and RS times alpha s. An expression of V is a word of W in W is a word W that consists of S1, S2, and so on. And we call the expression reduced if the length of W is n. We can also define the de Mazur operator for an element W in W with reduced expression W, that is S1 until Sn. And then the de Mazur operator of W is the product of the de Mazur operators of all the Si. With the following lemma, I will demonstrate that the de Mazur operator satisfies a number of important properties. And now let S be an element of capital S, and S is a simple reflection. And then delta S satisfies the following properties. There are more properties, but they're not important for us at the moment, so I will just demonstrate you those 6. So the first is that delta S is an RS bimodule map. The second is that S composed with delta S is again delta S, and delta S composed with S is equal to minus delta S. The third property is that delta S squared is equal to 0. So delta S composed with itself is 0. Then the fourth property is that for F and G and R, we have that delta S of Fg is equal to delta S of F times G plus S of F times delta S of G. And this means that the twisted Leibniz rule holds. The next property is that the set 1 and alpha S divided by 2 is a basis for R over RS, and has the dual basis alpha S divided by 2 and 1. And this is because of that the pairing F and G under S is sent to delta S F times G. And the next property is if we have S and T, 2 distinct simple reflections with MST smaller than infinity, that then delta S, delta S, and so on is equal to delta T, delta S, delta T, and where each side is a product of MST de Mazur operators. And this means that the braid relations are fulfilled. I'm not going to prove all of the properties since this would simply take too long and is not the topic of the seminar, but I will just quickly prove the second and the third property to make more clear how the actions S, the divisor operator, delta S, and alpha S, how they behave together. To prove them, we pretty much only need to do straightforward computations. First, we want to show that S acts on the divisor operator as a natural element if composed from the left. So you can see here how it works. If we take S of delta S of F, then this is equal, then we first plug in the definition of the divisor operator, and then we can use the fact that S of alpha S is equal to minus alpha S. So yeah, we get the minus in front. Then we use the fact that S of F plus G can be written as S of F plus S of G. So here S of F minus S of F can be written as S of F minus S of F. And S of F is, yeah, the same as F, because, yeah, we first see that S of F is equal to minus F, so we do that. Then we take the minus out, and then again we have minus S of F, which is minus minus F, and this is obviously F. So if we do all of that, we get F minus S of F divided by alpha S, which is, as we know, the divisor operator. And second, it needs to be computed that S acts on the divisor operator as the inverse of the neutral element if composed from the right. And yeah, you can see that here as well. And it basically uses everything from above, so it's nothing new. And for the third property, it is to show that the square of the divisor operator, meaning the divisor operator composed with itself, is equal to 0. And for that, it's also just a computation where in the end we get that F minus S of F divided by alpha S squared. So the first term is basically just no, the second term, S of F minus S of F divided by alpha S squared. This gives us like the first term, but multiplied by minus 1, so it cancels out and we get another important property that I want to mention is that delta W of F is equal to 0 if and only if F is W invariant, meaning that W times F is equal to F. An example to demonstrate that is the following example we've already looked at before. So let W be S5 again, and R the polynomial ring of R over the variables x1 to x5, and I the set of the 3 simple reflections. Yeah, we have again the same, that Ri is again a polynomial ring with those 5 generators from above, but now alpha S1 is here equal to x1 minus x2, and alpha S2 is equal to x2 minus x3, and so on. And the function S simply swaps the coordinates I and I plus 1. So now for Z1, which is equal to x1 plus x2, we can compute that that this is the same as delta S1 of x1 plus delta S1 plus x2. Then we plug in the definitions of the divisor operator, and then use the fact that alpha S1 is x1 minus x2. And then for S1 of x1, this is simply x2, and x1 of x2 is x1. So if we use that, we get 1 plus minus 1, which is equal to 0. And in the same way, it works for the other elements Z2, Z3, Z4, and Z5. And here I've just written down the computations for Z2 and Z3, it works more or less in the same way. For Z2, we need to use the twisted Leibniz rule and then get the same fact because the terms cancel each other out. And also for Z3 it's the same, but now we have three variables, but it basically works in exactly the same way. Since now delta Si of the Zi is 0 for all the i's, the product is also 0 of all those 5 de Mazur operators, and we can apply the property from above, and we get that Ri is S invariant. Next, I'm going to introduce the Bott-Samuelson bimodules. To do so, we need a few more definitions. So for S, an element of capital S, we let BS denote the graded R bimodule, which is defined to be the tensor product over RS of R and R with a shifting grading by 1. And BS belongs to RGBIM, and this means the category of graded R bimodules. Hence, all R bimodules that are finitely generated both as left and as right R modules. And this category has a shift factor for each integer, which sends M to M with a shifting grading of N. And yeah, so the N in brackets is the shift of grading by the corresponding number. So this means here the degree of one tensor product with 1 is, the degree of this is -1 because we have the shifting grading by 1. Moreover, it has a tensor product over R, and this means that the category of graded R bimodules is per definition a monoidal category. And what is important to notice is that the tensor product and grading shift, they commute. So this means that for graded R bimodules M and N and an integer N in Z, that we have the following canonical identifications, and you can see them here. It basically says that it does not depend on where we put the brackets. So yeah, it commutes, and we usually write Mn, but we mean M with the tensor product over R, like the tensor product over R of M and N. Yeah, an element in this BS can be represented as the sum over all I of the tensor product of Fi and Ji, and we can also replace the tensor product symbol with a wall symbol, and this wall symbol then should represent kind of a porous wall which only appropriate polynomials can pass through. And so yeah, we also use that sometimes, and we have that the following identities hold true. So F tensor product 1 is equal to 1 tensor product F, if and only if F is S invariant. And the module BS is graded free as left, respectively right R module, and its graded rank is V plus V to the power of -1, and all of this to the power of L. Hence, there is a connection between what we have learned about the Hecke algebra last week. And remember that after convention, 1 tensor product 1 has degree -1. So equivalently, 1 tensor product 1 and so on until like n times. This has degree minus the length of W, where W was our expression. The Bott-Samuelson bimodule corresponding to an expression W is denoted by BS of W. And this is the graded R module that is given by the product of all BSI. We usually don't write the tensor product, but we always mean that it's an iterated tensor product of all the bimodules BSI. Now, if W is the empty expression, then BS of W is the whole R. We can formulate a canonical isomorphism, which is that BS of W is equal to R with the tensor product over R as 1 with R and so on, where in the end we have a shifting grading of the length of W, which is n. And for that isomorphism, we basically just use the definition of the BSI. If we now look at an element of this BS of W, we see that they're of the form, again, as above, sum over overall I of Fi, tensor product Ji, and so on until Hi, for some Fi, Gi, and Hi, which are all in R. And here you can also see the notation, how it would look like if we would use the wall symbol instead. So let me do an example. Let W be A2, the alternating group of degree 2. Then the Bott-Samuelson bimodule BS of S1, S2, S1. That decomposes into the direct sum B S1, S2, S1 with the direct sum of BS1, which is then equal to BS1, BS2, BS1. And here we use that BS1, S2, S1, that this is equal to R with the tensor product over RW and R with a shifting grading of 3. And this is a submodule which is generated by 1, tensor 1, tensor 1. Yeah, we can also show more generally that if W is a dihedral group, which is generated by simple reflections, that like those two simple reflections, if they are S and T, and if we say that the length of W prime is smaller than the length of W, where we define W prime to be S times W, then BS, BW prime is equal to BW with the direct sum of BTW prime. And this is exactly like the general case of what I've shown above. Now let's talk about some properties about Bott-Samuelson bimodules. Let U and V be two expressions, and then we have that BS of U times BS of V is equal to BS of U V, where UV is the concatenation of U and V. This property means that on the one hand, Bott-Samuelson bimodules are closed under tensor product. If we look at those two expressions, that if we take F, multiply it by n GIs, which are all composed with the tensor product, like it basically says that it does not depend on whether we put the F in front or in the end, if F is in RW. So this fact basically says that every circle bimodule is actually in any Bott-Samuelson bimodule is actually an R tensor product R module. And yeah, I will now give you an example of an kind of easy calculation of the product of two Bott-Samuelson bimodules. And we first use the fact that R is equal to the direct sum of RS and RS alpha, as we've seen that before. And this is also equal to RS, the direct sum of RS and RS with a shifting grading of -2. And this follows from how we defined alpha S, and yeah. then we can rewrite the product of two Bott-Samuelson bimodules as R tensor product R, and then we rewrite the R that is in the middle, and we use the definition from above, and using that gives us that BS is equal to BS with a shifting grading of 1, and with the direct sum of BS with a shifting grading of -1. So notice here that this is analogous to the relation that BS squared is equal to V plus V minus 1 times BS, where BS is an element of the Kastan-Lustig basis. And yeah, we have seen last week that the Hecke algebra admits this basis. And yeah, we will see this again in the end in one of my examples. Yeah, so I've mentioned that Bott-Samuelson bimodules are closed under tensor products, but on the other hand, Bott-Samuelson bimodules are not closed under taking grading shifts or direct sums. We see this from the fact that BS is isomorphic to R with a shifting grading of 1 and the direct sum of R with a shifting grading of -1. And this implies that BS is graded free as a left R module. And in the same way, with the same computation, we can see that that BS is graded free when regarded as a right R module. And from this, we can conclude that the tensor products of bimodules, which are free of finite rank as left or respectively right R modules, that they're free of finite rank again as left or respectively right module. So from this fact or this lemma, we get to the next example, and this example together with the following lemma after this will state that any Bott-Samuelson bimodules is graded free of finite rank as a left, respectively right R module. So now if we consider the two elements CID, which is the tensor product of 1 and 1, and this is after convention and how we defined alpha S, this has degree -1, and the other element CS, which is defined to be 1/2 of alpha S tensor product 1 plus 1 tensor product alpha S, and this has degree 1. These elements form a basis of BS as a left or respectively right R module. Yeah, from this we can follow that those next two relations hold. The first one is that for any F in R, F times CS is equal to CS times F, hence it's commutative. And the second is that F times CI identity times S of F is equal to CS times delta S of F. And this can be verified by a simple computation. I will do this shortly. First, I want to mention that this relation, the second relation, is often referred to as the polynomial forcing relation. So I will show you that the polynomial forcing relation does indeed hold, and it's quite a forward computation. We just use the definition of the de Mazur operator, the fact that alpha S has degree 2, and the properties of the tensor product. So yeah, if we do that, first F times C identity, that's just easy. We just plug in the definition, and then we look at the second half of the equation, so the other side. And for that, we first plug in the definition, then we take out alpha S out of the tensor product. And yeah, after this, we can cancel out the factors 2 and the factors alpha S. And yeah, then we can cancel out that 1 tensor 1 S of F, because yeah, we have 1 tensor 1 S of F and minus 1 tensor 1 S of F. So this also cancels out, and what remains left is 1 tensor 1 times F, which is exactly F times the element CID. And these two relations I was just talking about, they allow us to relate the left action of R on BS with the right action and vice versa. So after all these definitions and lemmas, I will now introduce Soergel bimodules. Soergel bimodule is a finite direct sum of shifts of summands of Bott-Samuelson bimodules in BS-BIM, and this is the category of Bott-Samuelson bimodules. I will talk about this in a second, and one reason why Soergel bimodules are more useful than Bott-Samuelson bimodules is that Bott-Samuelson bimodules are not closed under grading shifts, but Soergel bimodules are. Next, I'm going to introduce the definition of the category of Bott-Samuelson bimodules, and this category of Bott-Samuelson bimodules, which we denote by BS-BIM, is the monoidal category, and hence it's a category equipped with a tensor product of R bimodules. And its objects are obviously Bott-Samuelson bimodules. We can also define the category of Soergel bimodules, which is we denote by S-BIM, and that's the strictly full subcategory of Z-graded R modules. And yeah, it consists of Soergel bimodules, meaning that the objects are direct sums of direct summands of graded shifts of Bott-Samuelson modules. Hence, the category of Soergel bimodules is the smallest strictly full subcategory of those RGBIM that contains R and BS for all S and capital S. And it's closed under tensor products, direct sums, direct summands, and grading shifts. To understand what the definition of a Soergel bimodule means, we need to know what strictly full means. So strictly full means that the category of Soergel bimodules is closed under isomorphisms, which means that it's the full subcategory of RGBIM whose objects are isomorphic to Soergel bimodules. To be said in another way, the category of Soergel bimodules is the additive graded envelope of the category of Bott-Samuelson bimodules. The upshot here is that in order to describe the category of Soergel bimodules, it's enough to describe the monoidal category of Bott-Samuelson bimodules. And in contrast to Soergel bimodules, this is an easier problem because we have concrete combinatorial realizations, so of the objects of the category of Bott-Samuelson bimodules. So that makes it easier. So now I will introduce some important lemmas and properties about Soergel bimodules. So first, Soergel bimodules are closed under tensor products, since S-BIM of U with the tensor product of S BIM of V is the category of Soergel bimodules of U and V, and U and V is here again the concatenation of U and V. And this makes sense since in the same way, the same was already true for Bott-Samuelson bimodules, where we saw that BS of U times BS of V is equal to BS of UV. And second, we reconsider the fact that any Bott-Samuelson bimodule is graded free of finite rank as a left, respectively right R module. We can also assume that for a graded left R module M, which is graded free of finite rank, any graded summand N of M is also graded free. So if we bring those two facts together, we get that Soergel that any Soergel bimodule is graded free as the left or right R module. Before ending up with some examples of Soergel bimodules, we need a few more definitions and a lemma. So first, let's look at the definition of indecomposable. An object M of an additive category, so for example, like bimodules, is called indecomposable if it cannot be expressed as a direct sum for two non-zero sub-objects M prime and M prime prime. If we now want to identify the simplest indecomposable Soergel bimodules, we can apply the following lemma. So if we suppose that M is a graded R module, which is generated as an R module by an homogeneous element. This then implies that M is indecomposable. So recall from the definitions before that an element M in M is homogeneous if it is contained in one of the graded pieces of M. We can conclude that R, the symmetric algebra of V, as well as BS, which we already know is defined as the tensor product over RS of R and the tensor of and R with a shifting grading of 1, that those two are indecomposable, but I will talk a little bit more about this in the examples later. And another result that I want to mention is that the category of Soergel bimodules is an additive category, such that every object is isomorphic to a direct sum of indecomposable objects. And such a decomposition is unique up to isomorphism and permutation of the summands. So now let's look at some examples of Soergel bimodules. I will now introduce Soergel bimodules in the symmetric group S3. So consider the polynomial ring R with the variables x, y, and z. Here we can also notice that we could replace the real numbers R with any field of characteristic different from 2, and the results would stay the same. Here also we have a natural action of S3 on R, and yeah, we here say that S, like the simple reflection S, interchanges X and Y. So in formulas, this means S times F of X, Y, Z is equal to F of Y, X, Z. And the simple reflection R interchanges Y and Z, meaning that S times F of X, Y, Z is equal to F of X, Z, Y. And so RS, which is the subset of R fixed by the action of S, is the polynomial ring over R with the variables X plus Y, X, Y, and Z. And RR, that works in the same way, is the polynomial ring over R with the variables X, Y plus Z, and YZ. So then the subring fixed by both the simple reflections S and R, which is also the same as for the whole group S3, is the polynomial ring over R, where the generators are X plus Y plus Z, XY plus XZ plus YZ, and XYZ. So yeah, those are all independent and generators. And now we can also take the grading into account. So we need R to have the usual Z grading multiplied by 2. So X, Y, and Z will be in degree 2. And the polynomials X squared and XY, they have degree 4. And for example, the polynomial 3x y squared z to the power of 7 has degree 20. And we defined the ring R shifted down by 1 by declaring that x is in degree 1 and x squared is in degree 3 and the other polynomial is in degree 19. The z-graded R bimodule R is the easiest example of a Soergel bimodule, and the second easy example, I've already mentioned that, is the Z-graded R bimodule BS. And other examples are the product BSR, which is the tensor product over R of BS and BR, and BSRS, which is the tensor product over R as R of R and R with a shifting grading of 3. And in this example of S3, the category of Soergel bimodules is the indecomposable set, which you can see here. But I will explain how this set after the next example. But at this point, I want to do a little comparison between the Hecke algebra and the Soergel bimodules. So we can think of BS, BS, BR, BSRS, and so on as analogous objects to the elements small bs, small bsr, BSR, BSRS, respectively in the Hecke algebra. And we can also think of the product, respectively direct sum, between Soergel bimodules as an analog of product, respectively sum, in the Hecke algebra. And shifting the degree of a Soergel bimodule by 1, that should be seen as multiplying the corresponding element in the Hecke algebra by V. Recall that the Hecke algebra H of S3 is free over the ring over Z with the generators V and V to the power of -1, and has the basis you can see here. So yeah. Now let's compose this set of indecomposables step by step. By definition, we already know that R, BS, and BR are distinct and indecomposable. What we should also remember is that R is generated by the subrings BS and BR. Hence, BS, BR is isomorphic to R tensor product R with a shifting grading of 2, and in the same way it works for BR, BS, which is isomorphic to R tensor product R with a shifting grading of -2. But in the first BS, BR, we first take the tensor product over RS and then over RR, and for for BR, BS, it works in the opposite way. And from these two equations, we can see that both are generated by 1 tensor 1, and this is obviously a 1 tensor. So this implies then that BS and BR, that they're not isomorphic. And and because we cannot express both of these elements as a direct sum of submodules of BS, BR, respectively BR, BS, they're indecomposable. And hence the product of the indecomposable elements BS and BR offer us two new indecomposables, BS, BR and BR, BS. So, but as shown above, BS, BS, which is isomorphic to BS with a shifting grading of 1, direct sum with BS with a shifting grading of -1, BS, BS is clearly decomposable. And in the same way, we can say that BR is decomposable, and we don't need to add these to the list of indecomposables. So the next step is to look at BSRS. BSRS is equal to R with a tensor product over R as R with R with shifting grading of 3. Then BSRS is generated by 1 tensor 1, and this has degree -3. And because of the isomorphism you can see here in the last line, that BS, BR, BS, it's actually in the category of Soergel bimodules, and this means that we can add it to our list of indecomposables. yeah, and since this isomorphism holds true, so that we can say that BSRS is isomorphic to BSRS, we can imply that BSRS is not isomorphic to any grading shift of the indecomposables that we've already found. So if we now try to multiply the bimodules with each other, we find that we cannot produce any other indecomposables. So hence the list of distinct indecomposables up to grading shift is complete and is given by the set here. So R, BS, BR, BSR, BRS, and BSRS. To see this comparison in another example, let us look at the following. If we want to show that the category of Soergel bimodules in our example S3 is stable on the product, we just need to prove that we can write any product of two elements of this set as a direct product of shifts of elements in this set. So first, one important fact about R is that if P is an element of R, then P minus S times P is an element of Y minus X times RS. So, for example, if P is the polynomial 3x y squared z to the power of 7 plus yz, then P minus SP, we can compute that, and we get that it's Y minus X times 3xy z squared plus z, and this is in RS. Yeah, the same result stands for R, obviously. So then P minus RP is z minus y multiplied by some element in RR. We can define alpha S to be y minus x and alpha R to be z minus y. Now, if we define P S of P to be P plus SP divided by 2, which is an element of RS, and delta S of P, which is defined to be P minus S times P divided by 2 alpha S, and this is also an element of RS, then we get the decomposition that P can be written as P of P plus alpha S times delta S of P. And this equality gives the isomorphism of graded RS bimodules that R is isomorphic to RS with a direct sum of RS with a shifting grading of -2. As a direct consequence of this equation, we obtain the isomorphism that BS is equal to BS with a shifting grading of 1 with a direct sum of BS with a shifting grading of -2. And we basically just get that by plugging in the definition of BS. But if we compare the isomorphism with the equality BS, which is equal to VBS plus V to the power of -1 BS in the Hecke algebra, yeah, we see a connection there. And we can also do that with the isomorphism that BSRS is isomorphic to BSRS with a shifting grading of 1, and the direct sum with BSRS with a shifting grading of -1. And yeah, again, we can compare that with the equality that works in the Hecke algebra. And yeah, we can see this connection to what we have learned last week. Also in the same way when doing that for doing the same computation with the isomorphism for all products in this set of indecomposables. So yeah, here we can see the connection between Bort-Samuelson bimodules, Soergel bimodules, and what we have learned about the Hecke algebra last week. And yeah, with this, I want to finish my talk, and thanks a lot for your attention.
Thank you very much for the talk. Any questions? Maybe you can go one slide back.
Mm-hmm.
Yeah, there are actually, it was a very nice talk, but there are a few typos in your slides, like in the second to last line. You definitely want to write VBSRS and not VDS. But anyway.
Oh yeah.
Yeah.
Sorry.
There are a few typos in the slides. That's not a big problem. But I think you forget to mention to tell us just one thing, namely the degrees of the elements in the polynomial ring are always 2. I think you never mentioned that. Okay. Don't worry, it's okay.
Okay.
Yes. Yeah. So what you see here on her last slide is that what we will see next week is that the category of Soergel bimodules should be a categorification of the Heck algebra. So everything matches. You have the same number of basis elements. You have the same multiplication rules. You have grading. Everything somehow corresponds 1-to-1. And next time we will actually see that it's actually true. And well, it's very explicit in some sense, but it's also a little bit complicated. So you shouldn't be too afraid if this was a bit too fast for you. It's very explicit if you sit down and do it. But well, after next week, we will get an even easier presentation of the same category. A really, really explicit one, really beautiful one. Okay. So I don't have any other questions. As I said, there are a few typos, but otherwise, thank you very much. And that's okay. So